In this video, we are going to be talking about rotational energy. So we still have all of the types of energy we had when we talked about it last unit. So we still have gravitational potential energy, elastic potential energy, internal energy, and regular, which the real term for it is translational kinetic energy. So the formula is just the rotational kinetic energy is equal to 1/2 I omega squared, where I is the moment of inertia and omega is the linear speed. So I just want to point out that I is the rotational version of m, and omega is the rotational version of v. So it makes sense that this is the formula. However, I want to go into it a little bit more deeply. Oh, and this is what the formula looks like on your formula sheet. So where does this equation come from? Well, let's take a particle on the very edge of this blade. And let's say that it is a distance r from the axis of rotation. So this little particle here is going to have a kinetic energy equal to 1/2 mv squared if we say that this particle has a mass of m. So we're also going to say that the fan is rotating, let's say this way, with an angular velocity omega. And remembering that v equals omega times r, remember this is the case because the further you are from the rotation axis, the higher the linear speed because you have to go more distance in the same amount of time. So then the particle would have 1/2 m omega r squared, which becomes this. And then you can rearrange it to look more like that. And then this bit of the equation here should look familiar. That should look like the equation for the moment of inertia. So if we take all of the particles in each of the blades, each of them will have this moment of inertia. So we're adding up all of the moments of inertia. So we would have 1/2 times the moment of inertia times omega squared. Omega squared is going to be the same for all of the particles, or omega is going to be the same for all of the particles because the whole fan has the same angular speed. So just wanted to go into more deeply where that comes from. Let's do some sample problems. A thin hoop with radius of 20 centimeters and a mass of 0.8 kilograms makes 4 complete revolutions every minute. What is the rotational kinetic energy of the hoop? The first thing we have to do is convert the 4 revolutions per minute into radians per second. So remember, this is the way you have to do it. We take 4 revolutions per minute, and then there's 2 pi radians in 1 revolution, and there's 60 seconds in 1 minute. So we see that these units cancel, and these units cancel, multiply everything on the top, and divide by the 60 seconds, and we get 0.42 radians per second. So we want to use our equation that we just learned for rotational kinetic energy. We have that this object is a thin hoop. If you look on your formula sheet or on the table of information for moment of inertia, you'll see that for a thin hoop, it is equal to mr squared. So we're going to go ahead and plug that in. So for m, we want to plug in 0.8. For r, we want to plug in the 20 centimeters, which of course we need to convert to 0.2 meters. And then 0.42 is the angular speed. So multiplying all of that together, you should get a small amount of energy, 0.00282 joules. And I just want to point out this makes sense because this hoop is not spinning very fast, so it's not going to have very much rotational kinetic energy. Sample problem 2. We've got 2 balls each attached to a light string. Notice that the outer string, or the longer string, is double the length of the inner string. M1 has a mass of 2. M2 has a mass of 4, so the masses are also double. And we know that this mass has a linear speed of 6.7 meters per second. So the first thing we want to do is calculate the rotational inertia of the system. So remember that this is the formula for rotational inertia. So for M1, we plug in 2. For R1, we plug in 1.2. For M2, we plug in 4. And for R2, we plug in 2.4. And you should get that the rotational inertia is 25.92 times kilogram times meters per second. Now we also want to find the rotational kinetic energy, and this is for part B. So now that we have the moment of inertia, it's pretty easy to plug that in there. But remember that this just gives us the linear speed at this point. So we need to find omega, or the angular speed. So the angular speed is going to equal V over R. So you just do 6.7 divided by 1.2, and you get 5.583 radians per second. So then you plug in those numbers that you just got, and you should get 404.01 joules. Now, I wanted to give this problem to point out why the formula for kinetic energy works. You could also find the kinetic energy of the two balls separately and then add them together. So let's do that. So the kinetic energy for ball 1 will equal 1/2 times m1 times v1 squared. So you plug all that in and you get 44.89 joules. And to get v2, or the speed of the outer ball, it's just going to be double the speed of the inner ball because it's twice as far from the axis of rotation. And we get 13.4 meters per second. So now we can plug all that into the formula for kinetic energy, and we get 359.12 joules. You add both of them together, and indeed, we've verified our answer by doing it a different way. Okay, sample problem 3. We have a frisbee with a mass of 0.175 kilograms and a diameter 0.266 meters. It's thrown in a game of ultimate. It can be modeled as a solid disc. In order to throw it, the player accelerates it from rest by doing 1 joule of work on it, causing the disc to fly off horizontally. We want to find the speed of the frisbee's center of mass and the angular speed of the rotating disc. So the work that the person does on it causes it both to rotate and to move. And it's the work that's causing the increase in kinetic energy. So in this case, the work is equal to the kinetic energy. It's giving us the work, and we know that this disk will have 2 types of kinetic energy. It'll have translational kinetic energy and rotational kinetic energy. So we plug in 1 for the work, and then just our formulas for the 2 types of kinetic energy. I'm going to multiply both sides by 2, and I'm going to plug in mr squared over 2 for the moment of inertia, just from your table of information. And I did something else. Remember that omega is equal to V over R. If you hadn't noticed, this is a very important relationship to remember while solving these problems. So I'm going to keep going with this. So once you put the squared on both these, notice that the r squares cancel. That's why I did not want to plug in numbers right away. Now, however, I do want to plug in some numbers, so I plugged in 0.175 for the mass in both places. And I'm going to solve for V. And I get that V is equal to 2.76 meters per second. So this is the speed of the center of mass of the disk. So if the disk is rotating and also moving, that's the speed that this is moving at. So we also need to do part B. We want the angular speed of the rotating disk. And again, we just use this relationship. We just do 2.76 divided by the radius, and it gives us the diameter, so we need to do that divided by 2. And we get 20.75 radians per second. Sample problem 4. What will be the speed of a solid sphere of mass m equals 2.3 kilograms and radius r equals 0.62 meters when it reaches the bottom of an incline if it starts from rest at a vertical height h equals 4 meters and rolls without slipping? So here it's just a simple case of the gravitational potential energy becoming kinetic energy, but this time we have two types of kinetic energy. So we're going to say mgh equals translational kinetic energy plus rotational kinetic energy. And I'm going to plug the formulas for those in. And it's a solid sphere, so the moment of inertia will be 2/5 mr squared. I'll plug that in. So now I can cancel out all of these m's, which is nice. Now we've got 2gh equals v squared plus 2/5 r squared omega squared. So what are we going to do about this omega squared? Well, we want this to be v over r. So, similar thing that happened in the previous problem. These r squareds will cancel. And I'm going to continue the problem over here. We'll have 2gh equals v squared plus 0.4 v squared. So the 0.4 just comes from the 2/5. Keep solving for v, and we get that v is equal to 7.48 meters per second. So I just want to talk about this a little bit more. When the sphere rolls down, any particle on the sphere will have a linear speed equal to its angular speed times how fast it's going, how fast it's rotating. So it'll be the distance from the axis of rotation times how fast it's rotating. So that's why in these problems you can plug v over r in for omega. And I also think it's interesting to point out that neither the mass nor the radius ends up mattering. So I want you to think a little bit about why that is.